so today we will have our first hybrid class. So basically, if you have, I mean, for online students, if you have any technical issue, you cannot hear my voice, maybe humming issue, this and that, please let me know. Maybe you can turn on your mic to speak or you put it in the chat box, okay? And for the face-to-face student, the same thing. If you have any question, you just raise your hand, okay? Uh, one moment, let me start recording first. Okay. Okay, so continue with our previous class. So we so in previous class for this chapter, we are actually looking into three different type of image manipulations. The first one is the point. I mean, just a small recap for all of you. The first one should be the point operations and followed by local operation and the transformations. So, of course, you would found that the end of this chapter, you will found that there is edge detections. In MTAA, image processing is, I mean, in terms of course, MTAA is a very bright, I mean, wide coverage. So in terms of MTAA, we have image processing, audio processing, and also the video processing. So in terms of image processing, as I mentioned before, I would emphasize more on image processing is due to the current trend of the engineering technology, because the image processing would have a lot of different vacancy in terms of image processing, but in terms of audio and also the uh, video processing, the vacancy, I mean not the vacancy, the how common is the engineering vacants is a bit less as compared to image processing. Okay, and in terms of image processing, we have different type of manipulations, and point, local, and also transformation are those very common. Other than that, you would found that edge detection. Edge detection is especially important in terms of non-destructive testing and evaluation. For example, you want to detect the edge of the you want to detect the edge. For example, you want to detect the age. You want to detect the age of a pharmaceutical medicines. So basically, why you want to detect the age in order to locate something else. For example, the most common example would be in semiconductor. You have a die, you have an orientation pin, you have the coding. Coding is like the number or the serial number for a specific lot. Okay, because in semiconductor industry, we always call, we have one batch of material coming in. So this batch, we call this as a one production lot. So the production lot usually come in a trolley lah. Okay, the trolley, they come in a trolley. So basically, one production lot, the the number could be various from 6K to maybe up to few 100K. Okay, I mean the number of unit lah. Okay, so for the entire lot, we call it as the lot lah. Okay, and usually the C 1, 2, 3 or maybe A, B, C. This number is to remark which lot it is from. Okay, and the orientation pin is to use. I mean, is meant to tell you what is the correct orientation. So if you found that the orientations is like this one, so definitely this die is being located at the wrong orientation. Okay, and also the reason why the die surface did have, I mean, printed with all these orientation pin, this and that, is because the image processing technology is being used in semiconductor machine industry for more than a decade. Okay, just that how advanced is the image processing techniques being implemented, that's all. Okay, so this is why they did have this all kind of printing in order to facilitate the vision detections. Okay, so that is why we always want to detect the age. The age, of course, sometimes the age could be this one. Sometimes the age could be this one, and sometimes the age could be everything inside the, I mean, within an image. Okay, so basically to detect the age, you can actually tune the parameter lah, and based on the practical, the lab practical, lab manual one, basically you already know there is several types of age detection method. For example, Pewitt, Sobel, Kenny, and Robert, and many more lah. Okay, so these are quite common method being used to detect the age. Okay, so the same thing, age detection is actually local operations. So that is why this is, I mean, but I put it in another subsection 4.3 to explain because it is something quite crucial in MPAA. Okay, and it is for age detection, it is actually in characterized under local operation as well. Okay, because you are still using a filter. You are still using a filter like this one. Maybe you can um, tailor the filter to make it to detect the age at the X orientations and tailor the uh, value within the window or the matrix or the canal to check for the Y conditions. Okay, which means because the H would be in run from X coordinate and also Y coordinate, which means the uh, edges in, you know, this is horizontal edge, this is vertical edge, right? Okay, so basically if you check the X orientations, check on this one, basically you will get a very light or very soft edge. But if you use the X orientation to check on the vertical edge, you will get a very strong edge. Okay, the same apply to Y. If you check using this, you will get a strong edge, and if you use this and check the vertical edge, you will get a soft edge. Okay, so one moment. So edge detections, extracting information about the image, their shape, size for information sharpening and enhancement. Edges are pixels in an image that correspond to object boundary. The object divide the region of distinct color. Basically, you can call something as an edge if the intensity is changed dramatically. What do you mean by change by dramatically? Something like this one. So the region here, I mean the intensity here would be remain more or less the same lah. And so the here. But for this region, I mean all this region, the intensity is changing from black to white, which means from zero maybe to gray and then to white. Perhaps the intensity will be somewhere around maybe 0, 0.5, 0.8, and then 1. Okay, so that is why the filter is meant to detect a strong changes in edges. I mean, a strong changes in intensity. So this is how the edge being formed. Okay. Okay. Bullet point 3. To find edges, the algorithm looks for pixel in the image where the intensity changed rapidly, which means you change significantly. If you have an entire image and the intensity from here to the very last point here change smoothly, maybe the intensity, I mean, like 0, and then 0 0.1, 0 0.2, 0 0.3 until you get 1, something like that. So you will found that no age, okay, something like that, because there is no strong changes. You can't really get a very I mean, you so-called an age at this smooth transitions pixel, okay. But if you have 0 0 0 1 0 0, then for sure this is the age lah, okay. So the age pixel would be somewhere around here, and so that is why it detects. We can actually see this as a step function. You know when you have 0, so you will get 0 0 0 and then 1, and then followed by 0 0 0. So this is sort of step functions like how what you all learn in control system. So the function h in MATLAB return a binary image containing the one where ages are found and 0 elsewhere. So which means the one which means the white intensity is referring to the age, and 0 is referring to non-age lah. Okay. So if you try to, of course, you can actually adjust the intensity by play around with the parameter of age lah. Okay, age, you can actually find age space MATLAB, or maybe Robert space MATLAB, Kenny space MATLAB, then it will appear the functions lah. Okay. So cameraman is a cliche example. So I equal to I'm read cameraman dot thief, and then you use the private age, and then you I'm show and show this original and also the one after you perform the age lah. Okay. Basically for this one, you store the result of age in BW1. Okay. So this is the original and this is after. So NH is a place of rapid change in the image intensity functions. If a pixel gray level value is similar to those around it, then most probably there is no edge. This is the hypothesis we have before we establish the algorithm. Because if there is a very slow transition of intensity, or none of the intensity change across a spatial domain, so basically we wouldn't say that there is any age lah. Okay, just like the bumper lah. Okay, if this is a very small hill, and the hill is rising up smoothly, and then going down again. So basically you won't call this as a bump lah. Okay, because you don't really feel a significance, a change in terms of the level of the ground, evenness of the ground. But if you have a bump, definitely something like that. So you can feel the bump and you have to slow down, this and that. So the same theory applies here. So if you have, let's say you have a very, this is white region, and then this is black region, white, black, and this is a small transition from white to black. Then it would be depends on the intensity or the threshold you use to detect the age. If you are using the Kenny, because Kenny is much more sensitive compared to Robert Prewitt and etc. So if you are using Kenny and you fine tune the thresholding, so perhaps you're able to detect these two age. If not, basically you will not able to detect, because there is like the same theory here. You a small hill and there is no bumper over there. So I mean the changes is not significant enough for the algorithm to recognize as an age. Okay. So NH is a place of rapid change. So this would be a very key that key features of the age. Okay, if you did not obey this one, rapid changes, basically there's no age. Okay, so if a pixel gray level value is similar to those around it, then most probably there is no age. And if a pixel has neighbor with large difference in gray level value, then it may represent an age. Okay, but sometimes this is not true as well. Okay, because it depends because most of again this is depends on your applications, because most of the time, for example, this image is an apple. This image is being corrupted by noise, maybe salt and pepper noise. So when we enlarge this image, the differences from this region and the so-called pepper noise. So this region is not an edge, but it will be detected as an edge because it obeys the theory or the philosophy of the edge detection. Okay, so that is why sometimes before you apply any edge detection method, it is advisable to smoothen out the image, maybe using Gaussian's median or mean filter. If not, you might misdetect those noises, for example, salt and pepper noise, especially as the edge, okay, which is something incorrect lah. So that is why sometimes you may need pre-processing in order to enhance the robustness of the edge detection method. Okay, so this is the example that we mentioned just now. So let's say this is your input image now. This is your input image. So you have a white color and then white color and black color at the center. So you have a transition here and here. Of course, the whole line. So the transition should be from, a white color and then light gray, medium gray, dark gray, and then followed by black color. So for this, the detection of edge is sometimes very dependent on the threshold given. Okay, if let's say the threshold given must be the differences from these pixels, this intensity to the next adjacent intensity is greater than maybe 0.02, then I will declare it as an edge, something like that. So if the difference is greater than that, so the line there would be declared as an edge. If the differences is keep on keep on obeying the condition declared by the user. So perhaps you will have a very thick edge. Okay, very thick edge. So if let's say the condition, maybe a very sharp edges, the edges must be, the differences in terms of intensity must be more than 0.05. So you will have a thin edge. Okay, so this is to check lah. The philosophy is actually just like the thresholding. If the intensity is greater than, let's say the threshold is 60 lah. If the threshold, the input intensity is more than 60, then you convert to white color. If lower than 60, you convert to black color. So the same condition as applied here. So if the difference of intensity for the current and the adjacent is more than how many pixels, so you will declare this as an edge. Else, this is not an edge, something like that. Okay. So sometimes when the declarations of, the condition that you set for the edge detections is quite loose. So perhaps you were able to get a very thick edge. Okay. And sometimes the edges is good for you, and sometimes the edges is not something that you want. Okay. So again, depends on the application, but I just let you all know you can actually cater this one or tailor the algorithm to fit to your desire. Like the assignment, right? You can actually apply the edge detection method, and you remove part of the unwanted edges, this and that. Okay. So this is the graph, so-called the graph. You can actually assume that white color is 1 and black color is 0. So this would be the transitions. This would be the transition at this point, and this would be the transitions for this point. Okay, and then become white again. So white is 1, right? So black is 0. So this is how you get this graph lah. Okay, and from here, from here and here, when you get the second derivative, first derivative, you will get something like this one, and perhaps later on you can convert this as the edge. Okay, so if not mistaken, for second derivative, you will get a line cut through this one. So this would be your edge lah. Okay, we will learn this later on in the subsequent slide. Don't worry. So edges are more model according to their intensity profile. So step ages, step age, RAM, and roof. It is not suitable. It is not unusual to find image that contain all three types of ages. Basically, step RAM and roof, roof would be very quite rare, I would say. But for step and RAM, step is something like this one, right? And RAM should be something like this one, right? So for step, which means what kind of ages will show a step response is that the intensity difference is very significant. For example, 0, 0, 0, 1, 1, 1. So you would expect a step response, right? And for the RAM, which means you have 0, 0, then maybe 0 0.5, 0 0.6, 1, 1, 1, 1. So perhaps you will get something like this one, which means this is a transition. So by looking at the step or the RAM functions, basically you might have very strong edges or very soft edges. Okay, and if the thresholding of your or the setting or the parameter of your age detection algorithm is not strong, which means you might have a very thick edges here because they will consider all this part as the age. And for this one, you will get a thin edge because only this line is the age. Okay. And yeah, perhaps in one image, sometimes you might have all these three, okay, but roof would be very rare. Okay, so this would be the step, RAM, and also roof. Basically, roof is like a roof. This is a roof. It is actually a combination of two RAM. Okay, going up and going down, but the transition is very small. But this kind of most of the time, this kind of graphic would be those that already being image processed, already being processed by some of the algorithm. For example, you have detected the age. For example, you have a white color, and then uh, you know this is the age, a grid line. So and this line is very thin, so you will get something like this one, roof lah. Okay. Okay, so ideally, this is how the step and RAM looks like now. And for the roof, basically you can assume something like this one. Continue here, and you might have a shading back to black color, something like that. Okay, so basically, roof is more or less similar like the RAM functions. So as I mentioned just now, you can actually assume the black color is 0 and the white color is 1. So this is how you actually plot the graph, which is a step response. And for this one, you can actually plot a RAM response. And for those that shading to become black color again, then you will able to get a RAM response. Okay. So ideally has abrupt abrupt changes in brightness. So each appear very distinct. And for this one, uh, why I say this is ideal, this is a real, because usually only in synthetic images you would have ideal ages. Because for example, you have a checkbox. So this is a black color, black color, black color. Usually only this kind of synthetic image you would have ideal age because you define the intensity significantly one by one, like 0, 0, 0, 0, and 1, 1, something like that. So from uh, the 0 and 1, the boundary of each checkbox, so you would have a strong edge. Okay, but in real case, when you use a mobile phone to snap an image, and all those edges, no matter it is no matter how strong is it, uh, a black object with a white background, you will still cannot get an ideal edge like this one. Okay, that is because of course this is very relevant to the capacity capability of the mobile phone or the DSLR or any image acquisition machine or device. Okay, because most of the time, even using a very high quality DSLR, we cannot get a very, you know, clear edges from one object in conjunction with their background. Okay, so this is why in real cases, usually we will have something like this one, okay, which is a RAM response. Okay, uh, perhaps how step is the RAM response, then that would be how great the contrast is. So if you have, you know, a black object with a very with a bright or white background, perhaps you will get something like this one. I don't know, something like this one. Okay, so the transition period would be expected to be smaller, smaller, and smaller. But in ideal case, you will get something like this one. But most of the time, you will get something like this one. So if your image is very blur, the definition is very low, resolution is very low, you would expect to get something like this one. Okay, so if not so possible to get a smooth line because if smooth line which means no transition, okay, that is how actually you can interpret the data from just the step diagram or the shading of the uh, image. Okay, sometimes as I mentioned before, the image processing, if you are interested to venture into image processing, most of the time image processing deal a lot with the mathematical equations. Okay, of course you don't need to know the mathematical equation in depth, but for you all to, you know, better incorporate maybe new method, new proposed method, this and that, the best is to have some understanding, I would say, because I myself is not a person that very strong in mathematics. But nonetheless, when you work in image industry, I mean image processing industry, so you will find that actually many things is derived from mathematical equations. Okay, so that is why in most of the, I would say almost all, you are actually doing something else which is derived from mathematical equation. No matter for thresholding, FCM, k-mean, any other enhancement method, even the deep neural network, the black box, the adversary attack of the deep learning and etc. You are actually playing around with the mathematical algorithms and the equation as well. Okay, so at least you have to know a bit lah. I mean, you know, should be okay, no issue lah. Okay, so and also we will need to learn, not learn but we need to know the application of integration and also differentiation, where we learn in Form 4 or Form 5. Okay, so basic 4 step in edge detections: filtering, enhancement, detection, and localization. Basically, this would be the common step in, I mean, before perform edge detection. Because as I mentioned just now, if you did not perform filtering, you might have, I mean, the input image might suffer from different kind of noise, and the edges detected might not be so promising or not something that you want. Okay, so that is why usually in edge detection we will apply filtering, either mean filter, Gaussians, or maybe median filter to smooth out the image. So of course, the intensity of, you know, the intensity of applying all these filter cannot be too high, because if it is too high, as you all know, the mean filter, Gaussian filter, and also the median filter would reduce the, I mean, would blur out or smooth out the image. So if let's say you apply the median, mean, or Gaussian filter at a very high degree, or using a very big neighborhood, for example, 9 times 9 or maybe 15 times 15. So basically, you would expect your image would be blur out later on after you apply the filtering. So if let's say you blur out most part of the images, so it's very difficult for you to perform edge detection. Okay, although the image is, you know, like no noise, it's smooth, but it's very difficult for you to create the edges from a smooth image. Okay, so when you apply this, do aware this, and and I do like to ask questions like this one. Okay, just for your information. As I mentioned before, I seldom ask you all to please define age detection. I seldom ask questions like this one. Okay, so I would ask something like that. Require you all to think and connect between different fundamental knowledge. Okay, I seldom, because I don't think of course now there might be some, maybe one or two questions with very low marks for you all, earn for free. Those please define this, define that, because at the end of the day, I believe after graduations, maybe few months after the course or program, you won't be able to remember already. So basically, if you have handphone, if you have computer, if you have Google, you can always Google it out. Okay. So to me, all these kind of, you know, those info knowledge or that require memorizations is not my main interest. Okay. So I would like to test you all more on how you justify reasoning this and that. Why this, why that, something like that. Okay. If to me, because this is a senior year course now, of course. If this is a junior year course, perhaps I will test more on uh, knowledge, understanding, and this and that. Okay. Else, I will test more on um, justifications, higher cognitive level at least. Okay. So back to here. First thing to do is to do filtering, and then enhancement, detection, and localizations. So filter image to improve the performance of each detector with respect to noise. So this is what this is the main purpose lah. If the, of course, if the image is very, very clean, so basically you can skip this step lah, because anyhow when you apply an image processing algorithms, two things would be important. First of all, it require RAM, okay, random access memory. So if let's say you have one image, then should be fine. If you have thousand and million image, so maybe one of them take maybe 0.01% RAM. So if you have 1 million, then how many RAM is being taken? But of course, the RAM is a random access memory lah. It will not, permanently occupy that. Then the second thing is the time taken, especially in the semiconductor industry. We always talk about UPH, which is a unit per hour. So a very expensive non-destructive testing and evaluation machine should have higher UPH. So basically, when of course, this is if you have a company, when you buy the when you buy the machine, you always ask what is the UPH, and eventually you go to the website from Vitra, MIE, Panda Master. They will always mention the UPH of the machine. So you would expect higher UPH would have higher price. Okay. So that is why UPH is very important here. It's also more or less proportional to the price of the device. Okay. So when you have high UPH, which means you can inspect more device in 1 hour. Usually we will check, we will measure it per hour, like unit per hour. Okay. So if the filtering, the filter image pre-processing algorithm take maybe 1 millisecond. So if you have in 1 hour you have occupy how many milliseconds? Okay. Usually in the semiconductor industry, everything is calculated or measured in millisecond. Okay. So if let's say you occupy 2 milliseconds, and this is, the filtering is not necessary lah. So you have waste 2 milliseconds for each device. Okay, something like that. So if you have up to million device, so how many milliseconds you already waste? And this will greatly reduce the productions. Okay. So in terms of production line, uh, if the production line stop for productions, the moment the production line stop for production, that is the moment the production line start to lose. Okay. So this is how they actually calculate the benefits of the production line. The production line can be never stopped. So that is why people say that those production line like mini circuit, like Jabil, all those production line usually will not stop until I think 1 week in a year, which they need to do the audit and etc. Of course, due to COVID, maybe they have to stop something like that. Okay, so this is how they actually manage. So if the production stop due to some issue, that issue must be very significant and must be highlighted. So here comes the stress. Okay, and then enhancement. Enhancement is to enhance the pixel having significant change in local intensity. So after we smoothen out the image, we want to enhance the edges. For example, if you smoothen out let's say you have one image, so you have a circular shape. So you maybe have yellow intensity inside, something like that. So in order to detect this edge, you can always enhance the a particular intensity. For example, if the intensity is between A and B, so you want to multiply the intensity or divide the intensity by something else. Still remember, I'm not sure if you still never remember the very beginning of this chapter, we have, by the x input divided by 2, right? Or 2x, right? So let's say x is your input intensity. For example, you have intensity of 100. So 100 divided by 2, which means you have now become 50, right? Or 100 multiplied by 2 will become 200, right? So which one would have a darker pixel, darker color? 50, right? Because 50 would be approaching to 0, right? So 0, 50, 100, 200, and 255, something like that, right? So after apply this one, you would expect to get a darker edge, or I cannot say darker edge, darker intensity, okay? And if you apply this one, you would expect to get brighter intensity, something like that, right? Okay, so if let's say the transitions for this and adjacent pixel is greater than how many pixel value, so you want to divide by 2. And if I mean if else I mean else conditions, you will multiply by 2. So by using this method, you can actually enhance those pixel or those intensity with significant decrease or significant changes in terms of intensity. Okay, so this is the enhancement I meant here. Of course, the enhancement I meant here will be in a general terms, because there is no such the strict rules that, oh, the enhancement must be implemented by using A or B, something like that. But the enhancement is just meant to highlight the object of interest. If let's say the object of interest is the circular shape, so you can do whatever things or whatever algorithm to enhance the circular shape in your input image. That's all. Okay. So there is no solid algorithm to perform that. Okay, any algorithm would be fine. The main purpose is to enhance the object of interest. So detection will be the core the core in edge detection, because you apply the filter. And localization is to localize the position of the field of the edge. Okay, if this is the edge, you will localize this accordingly. Which means after you perform the edge detection, the circle will not, the edge will not be here Okay, it must be somewhere around here which is matched with this one Okay. Still remember in previous, I think in this chapter as well, we did apply the enhancement, right? We perform Laplacian and then get the edge of the cameraman, right? And then later on add into the original image to enhance the contrast. So this is another common method for you all to play around, especially when it comes to image enhancement method Okay. um there's no stringent rules in image processing. You can do whatever things as long as you can get the desired output, then would be fine. Okay, so among the popular edge detection techniques, you have actually 5 methods. Okay, first order derivative, which is the gradient method, second order, and optimal edge detections. So from here, Basically Robert Pivot Sobel, Laplacians or Laplacian of, sometimes we call it as LOG lah. Okay, in most of the paper we call it as LOG lah, Laplacian of Gaussians. I would say that LOG would be something quite common to researcher lah. Okay, because um yeah, because most of the time I think they did use LOG to, because the application of LOG is quite wide. Not only to detect the age, you might apply the LOG, Laplacian of Gaussians, to detect a particular features as well. So sometimes they will use the LOG lah. Okay. Of course, what you have to know is first derivative, second, and optimal lah. And those names are quite significant. I think it's easy to remember lah. Okay. Robert Previtt, Sobel, Laplacian, and Kenny. Anyhow, Kenny is the optimal age detection method lah. So anyhow, all of these are still using the filtering method, which is a local operation. So use gradient of intensity. This is the gradient function, and the gradient method detects the edges by looking for the maximum and minimum in the first derivative of the image. So first derivative tell where is an edge, where an edge is, and second derivative can use to show edge direction. Okay. To show the edge, I mean, first derivative is to tell you that this is an edge, but second derivative is to tell the, what direction the edge is going, x direction, y direction, and etc. So you have x and y, right? So basically, the second derivative will tell you from where to where. For example, something like this one. So the edges is going upward like this one. If you have something like this one, so the edges is going somewhere like this one, okay, from top to bottom and bottom to top. So let's say this is an example, the profile. This is the profile. Profile which means this is the input image, and this will be the profile. And what profile this? What profile it is? It is a RAM. Okay, RAM functions. And then from this RAM function, you can actually assume this is 0 or black color, 1 or white color. So there is a transition here, and this would be the profile. Okay, and first derivative, you will know, oh, this is an edge. And then second derivative, you will know the direction of edge. Okay, so zero crossing, they will check for zero crossing, cross the exit. So from there, they will try, the algorithm will try to know the directions of a particular edge. So magnitude of first derivative can be used to detect presence of an edge of at a point, and second derivative properties produce two values for every edge. Two value, this first and second. Its zero crossing can be used for locating the center of a thick edge. So if you only stop at here, perhaps you will have a thick edge because the edge would be here. So you would expect your image, this is the edge, very thick. Okay, if you stop at first derivative. But if you stop at second derivative, if you find the crossing line, then perhaps later on, this is your edge, and this is the original first derivative. Okay, so something like that. So approximations, what is this? Okay. Must be 0 in the area of constant intensity, must be non-zero and on-site non-zero at the point. Basically, this is like what I explained just now. Okay, so this is a step, and this is a roof. Because when you have only, if you have only ideal case, in ideal case, you have a step input image, so your profile would be something like this one. So this is your profile, and from this profile, you will need to calculate the first derivative. You will get a one pick only lah. Okay, if you have a smooth transition, you will have two pick lah. Okay, this is one, this is another one pick. So later on, from this, you will get a second derivative. So the edge would be very close to here lah. So basically, for this case, the edge would be very I mean, even the output result from first derivative and second derivative will be more or less the same because the h is very short. Okay, but for this one, this is the profile, RAM case, RAM edges. So after that, you will have one here, and create this, and then later on, this become one sharp edge. This is another edges for second derivative, and the cutoff would be somewhere around here. So this would be your edge lah. Okay. So for this case, if you stop here, you will have a thick edge. If you stop here, you will get a much more thin edge. So image gradient, first order derivative. Still can recall, we have different kind of edges here. First order would be Robert, Prewitt, and Sobel. Second is LG, and the optimal is Kenny. So now we start to look into different order derivative with different functions. Okay, the tools of choosing the tooth of choice for finding edge strength and direction at location xy of an image is the gradient. So basically, the gradient is to know the change in the line. Okay. Again, this is a mathematic. Recall back to form 4, form 5. To get the gradient. So basically, it's the line. Gradient is actually the line. Okay. To calculate how strong is the gradient, and from the gradient you can calculate the magnitude, this and that. Okay. So the tools of choice for finding edge strength and direction at location xy. Okay, so basically, I don't need you all to memorize this one. This is just general equations, to show that this is the function, the gradient f. So the magnitude from the gradient, just put on this sign, you will get the magnitude. Basically, x squared plus y squared. This is how we get the magnitude, right? Just that we apply the magnitude in terms of the gradients. Okay, the gradient vector at a point xy is given by Euclidean vector norm. Euclidean method is actually, there are many types of method to calculate the distance. Euclidean method is the simplest one. For example, in Chemin, if not mistaken, FCM also the same, but it's similar. So they are actually calculate the Euclidean distance. What is meant by Euclidean distance is that, you can imagine this is a Cartesian plan. You have a x point, you have a y. I don't use x and y, a point and b point. You have an a point and b point. So you have a xy, right? Ay and bx, by. Okay. So the distance between these two, sorry, should be these 2 points. These 2 points. This is the Euclidean distance. Okay. So basically, we all know that this is Euclidean distance since I think from 4 or from 5, but you don't know that this is actually Euclidean distance. Okay. Euclidean distance is being used in calculating the Chemin, and of course, there are much more. Many more different kind of distance calculations available. For example, Mahalo-Bini's distance, and this and that lah. Okay, if you are interested in terms of play around with Chemin, play around with FCM, you can actually change the way they are determining the distance, and then to check if the overall performance could be improved or not. Okay. So the direction is using the negative tangent, arctangent. So you will know the directions. So again, as I mentioned just now, when we try to detect the age, it has x orientations and y orientations, which means you have a horizontal and also the vertical, or x or y. Okay, so basically, if you have you have this in your image. So if you are using if you are going to check for vertical directions, so you will be able to detect only this one. And if you check at the vertical direction, you will able, horizontal direction, you will get only this one. Then you combine these two and you get this one. Okay, so this is how we actually perform because the window, anyhow, at the end of the day, this is still a local filtering. So which means you are trying to apply a window and you still need to perform uh, zero padding, reflection padding, or mirror padding. And then you apply the window from this to another next window, next window, next window, and continue. Okay, so your window would be performing at zigzag directions, or maybe this, start from here, from here, from here, until complete the entire image. Okay, so this is why, and we are not going to move the window randomly, randomly direction. So that is why we always try to check something in X orientation or Y orientation. So if let's say this filter is meant to be checked in the horizontal direction, so we will check for horizontal direction first and then followed by vertical direction. Okay, so this is how we actually apply, alter the filter to cater for different applications. Okay, so the gradient is a vector which shows the direction of change in the intensity X and Y direction. It has magnitude, which shows the strength of the pixel change and also the angle. So basically, these are the two important items in each directions. Gradient is to know X and Y directions, which is the directions. And the magnitude is to know the strength of the edge and also the angle. So you will have something like this one. Sometimes, not sometimes, the differentiation df and dx is actually referring to a small change. This is a symbol to refer a small change of something else. Okay, it is actually differentiation. Okay, I think it's called delta one. Okay, so this is to check the x orientation, y orientation, and this is both the orientation. Basically, you combine this and this, you will get this one. Okay, so before we proceed, maybe we take five first. Okay, we take five and then we will continue at page 85. Class, we will have a replacement class this Thursday, which is 17th of February, 2 to 3. Okay. Uh, this replacement class is meant for, yeah, this replacement class is meant for 23rd of March. Another thing to let you all know is that for week 7, in week 7, which is starting from 28th, right? One moment. We have class on 1st of March and then 3rd of March. So 1st of March, we will have our lab and also 2-hour class. And 3rd of March, we will have 1-hour class only. Okay, no tutorial because that is week 7. So for Tuesday, we will have online class for both the practical and this lecture class. And for 3rd of March, we will do replacement by this Thursday. Okay. The reason why is that I'm outstation for that week. Okay. So I heard that some of you wish to use the lab for practical class. I wish to know the number, and if let's say you want to use the lab, maybe I can let the technician know lah. Okay. But of course, if you all want to use the lab, first of all you have to let me know the number of students, and also, uh, yeah, the number of students should be sufficient. But we are not using Q002 because in the timetable we should be using Q002, right? Because Q002 now we are on the progress to purchase a new MATLAB license. So after that we will have the latest version lah. Okay, but for now we are in the transition period so we just brought in for Q02 we are now having new PC already. So all new PC and I think 2 or 3 high performance PC over there you all can use. Just that now at this moment don't have MATLAB yet lah. So we are trying to put already in progress to purchase the latest MATLAB. So for this moment, if you all need to use the lab, we are using D109B. Okay, let me put it in the chat box. Okay, we are using D109B. Okay, so yeah, you can the one who responsible the lab technician would be Mr. Razvin. Okay. So let me know first if you all need to use the lab earlier. Okay, maybe few days you can ask GA to tell me. Okay, so I will let the lab technician know. But I think the cap will be around 15. I'm not sure because I never been to this lab yet. Okay, Q002 I know but Q002 is not yet equipped with the lab. So that is why Okay. So let me know earlier, and I can do the arrangement accordingly. And yeah, never mind. Later I will post the replacement class informations in the Google Classroom later on. Okay. Just for those that attend physical class, we have class 202, M202, and then later on 203. Okay, because 202 there are some people using later on. Okay, so that it is. Any questions? Any question? No. If you have question, feel free to ask. Okay, so let us continue. So we continue with the gradient operator. Yeah, basically I don't really, I mean, you have to maybe you just need to know like the gradient operator this and that, but I won't really test or please write the gradient operator or something like that, okay? Or from the gradient operator, I ask you to calculate this and that, because I understand in later on uh, we are still using MATLAB, other software to do this. What I want is that you know that, oh, I know what is Sobel doing. I know what is Kenny doing. That's all. Okay. You don't really need to know, this one, this and that. Of course, later on, if you want to uh, do more research in terms of improvement of the Sobel Kenny, then of course, but that is next level. But for now, I think should be sufficient for you all just to know what is Sobel doing, what is LOG doing, this and that should be sufficient. Okay, so this is the gradient operator, but of course you have to know there is always x and y. There is always x and y because you have two different orientations to detect the horizontal edge and also the vertical edge. So the approach frequently used to approximate the magnitude of the gradient by absolute value. So this is basically the magnitude. So the each pixel can be located by finding the large gradient magnitude. So basically, the highest or the most significant magnitude would be your edge. So noise in an image can be create problems. As I mentioned, if you have, salt and pepper noise, so basically, when you have the gradient operator looking at the horizontal to get the vertical edge, or in another, in the y directions, you will recognize this one as the edge. Okay, so that is why noise in an image can create problems and should eliminate or at least minimize in an image. So need to accept the trade-off between sensitivity and accuracy of edge detection. So this is something that you need to, the trade-off lah. Okay. For example, you want to buy a very, very good handphone and you want it to be very, very cheap. Basically, it's not possible lah. Okay. You have to know the trade-off. Of course, sometimes it's due to the brand itself. Sometimes due to the brand itself, the price would be sky high. But sometimes if you want very high performance computer, like let's say you want a very high performance computer, a very good RAM, you run with SSD, this and that, but you want it to become less than 2K, it's likely to be impossible. Okay, so this is the trade-off you want. So if you want to have a budget like 3K, basically you can have moderate features, moderate RAM, depends on which one you prefer. If you say, oh, I want SSD, so you go for 5 GB SSD, and maybe your RAM should be reduced a bit because RAM is very expensive. Okay, so this is the trade-off. We always play around with the trade-off. Depends on your application as well, because the sensitivity is how sensitive you can locate the edges, but the accuracy is sometimes not there. For example, you apply filtering in order to smooth out the noise, but when you smooth out the noise, sometimes the edges will be smoothed out as well, especially for those soft edges. Okay, it's very hardly for you to identify this edge, but after you apply Gaussian's median or mean filter, it's harder for you to get the edge. Okay, but this but if you don't apply the filter, you might get all the edges and also all the edges which is a result from the noise. Okay, so this is the trade-off you need to play around. For example, like the thresholding lah. If you apply thresholding, if the thresholding is too low, most of the intensity in the image, input image would be considered as object of interest. If the thresholding is very high, so it's less likely you hardly to threshold anything else after the the output image is likely to have anything else. So you need to find the optimal threshold image. Optimal threshold value. So the same thing here. So too sensitive detect more points, detect noise point. Okay, which is the point that one is not the age lah, but the actually it is noise lah. Okay, and less sensitive might miss valid edges. And larger mass, less sensitive to noise, and low gray level threshold, reduce noise effect. Okay, so these are the trade-off. So without the noise, this is with high, I mean, um, corrupted by noise. Okay, so ideally you would have something like this one, and then by increasing, actually this is increasing in noise, but not so visible here. So if you have a noise level, a very high noise level, basically after this is first derivative, this is second derivative, this is the images and the profile. Okay, so after the first derivative, you would find that because for first and second derivative, the details of the image would be amplified. Okay, so that is why in the first row, the first column from the left hand side, you will find that actually you cannot really see a lot of noise over there. But then later on, in first derivative, you will find that there are noise all over. I mean, distribute all over the image, which means you have noise here, noise here, noise here. Of course, this the first one no noise. Okay, and then later on after the second derivative, this is actually the peak. Okay, should be somewhere around here lah. This is where the case is corrupted by noise. So later on, another one, you are hardly to get the edges lah. Okay, and then later on for this one, to be frank, it's very difficult for you to get the edge lah. And the bottom one would be the worst. Okay, so this is how noise being, I mean, how the noise corrupt this, how the noise corrupt the algorithm of edge detections. So convolution is an important and popular techniques in signal processing. Each can be found by convoluting an image with a mask. The formula is represented by this one. So basically, this is the gradient operator. The P is the P prime. This one is the output image obtained from the convolution operation. M is the filter mask. Where is M? This is the filter mask, and P is the input image, which is this one. Okay. So Robert operator is one of the simplest and oldest method of edge detection. Work best with binary image. Binary image, which means the image is only black and white. Okay, 0 and 1, which is only 2 bits. Mark edge point only does not return any information about the edge orientation because the Robert is first derivative, which means the first derivative only mark the edge lah. It will not tell the directions of the edge because the direction of the edge could be told by the second derivative only, which means LOG. Okay, so the Robert you can only mark the edge lah, but can be detect the low image at low noise level with thick borderline. As I mentioned before, because it is only calculate until first derivative lah. So which means the edge is always very thick lah. Only if in second derivative, so you would have a thinner, the line could be thinner lah. Disadvantage, localization is not good and weak respond to January edge. January edge, which means the edge which is very soft lah, like the texture of the wrinkles and this and that lah. The texture of the hair, which is quite soft lah. So this is an example. This is the input image, and this is the output of the Robert operator. So as you can see, the Robert operator cannot really detect, all this line by line, but instead, it will detect, for instance, something like this. It will detect this as one line, this as one edge, and this as another edge. Okay, so this is why the line here is different from here. Okay, and as you can see, the light bulb, the edge of the light bulb cannot be detected well. Okay, because the top part of the light bulb is quite soft for the edge. So and the intensity is more or less same as the frame. So that is why unable to detect this as the edge lah. Okay, but for those a very significant difference. The ink and also, is it ink? The brush, and the white color frame, so it can be detected with very thick edges. Okay, so this is the result lah for Robert, as well as the eye, the makeup here. So it's very obvious. But you see, the hair texture is not obvious. Okay, so this is the shortcoming and also the advantage of the robot. And Sobel is also the first derivative. Look for edges in both horizontal and vertical direction, and then combine the information into single matrix. So for Sobel, it will read the x direction and y direction, and then combine both to become one image. So Sobel is sensitive to high frequency noise. The masks are given as this. Okay. What is meant by high frequency noise? We will learn about high frequency information in next chapter. Okay. High frequency information is that the details. For example, the texture of the hair, the wrinkles, the sharp edges, all these details are considered as high frequency information. What are the low frequency information? Which means those intensity did not have any significant changes. For example, this is an image with apple, right? Okay, so at the edge here, those intensity that represent the edge, the water droplet on the apple, the shining, the great details, some of the scar remain on the apple. All those details or the texture of the image are considered as high frequency information. So what are the low frequency information? For example, the intensity of the background, the intensity of the apple, which means the intensity, the transition of intensity is very low. For example, this is a red apple, right? So maybe the intensity for RGB, the R value maybe is 200, 100, for example, and then the adjacent one is 201, 100, something like that. So the changes in terms of intensity is very, very small. So those are considered as low frequency information. And you have to know that if we remove the high frequency information, we still able to interpret the image. For example, you have an apple, image with apple. If I remove all those high frequency information, you will find that, oh, this is an apple, but this apple looks very blurred, something like that. Because the details of the shape, the water droplet, the all those wrinkles or scar or any other things on the surface of apple is not so visible. But if I remove all those low frequency information, you might no longer can describe this is of apple, because the red color intensity, the background, all being removed. Only all those, high, the texture, the line remain only. And the output may not be exactly like the edge detection. Okay, so please do not think that, oh, so if I remove the low frequency information, I can get the edge lah. No, this is not true. We will explain more about this one in chapter 5, which is the next chapter. Okay, because for next chapter, we will learn about the high frequency information and low frequency information, and how do we actually convert this frequency, the spatial domain, to this Fourier transform. We call this as Fourier transform. Okay. So let's continue. The Sobel, okay, we back to here. The Sobel is sensitive to high frequency noise, which means if you have noise such as the salt and pepper. So if you have salt and pepper noise and you apply Sobel, you would expect to have a very bad quality edge detection output because this Sobel is quite sensitive to the high frequency noise, which means all those noise in texture, sharp line, all those are very easily captured by Sobel operator. So the Sobel gradient operator Gy compute the gradient in the y direction horizontally, and Gx compute the gradient in the x direction vertically. Okay, so Gx and Gy are obtained by convoluting the image I with the gradient operator, and Gx gives the horizontal gradient magnitude, Gy gives the vertical one. So which means x is referred to horizontal and y referred to the vertical. Okay. So later on, you get the magnitude to get the output. So in terms of this is the input image. So if you check in terms of x directions, the gradient in x direction, you will get the vertical edge. If you check in the y direction, you will get the horizontal edge. So as you can see, all these edge are more on the horizontal right, and all these straight line are more on the vertical right. So that is why it's hardly for you to get the vertical line here, but you can get very detailed vertical line here. Okay. Of course, sometimes you may ask why they are still got edge here and edge here, because sometimes the edge is defined by pixel, and the pixel is not a must, exactly like what we can see lah. Okay. So this is the difference for that. So anyhow, for y direction, you're able to get the horizontal edge. For x direction, you're able to get the vertical edge. Okay. So the same apply here. And this will be a bit obvious that. So if you're x direction, you will get vertical edge. Y direction, you get horizontal edge. So this is the vertical edge. Okay. So it's very obvious here. But in here, the vertical edge is not so visible. So later on, you combine these two. So you get the edge image for this input image. Okay. So compare the output of Sobel operator with Robert operator. The subroutes edge are still present, but they are relatively less intense compared to genuine line. Robert operator has mixed a few edge, and Sobel operator detect thicker edge. So this is the comparisons. This is the input. This is Sobel. This is Robert. Okay, as you can see, the Sobel edge is much more sensitive towards the details. For example, the texture of the hair. Basically, the Robert is not so visible. Okay, and recall back, Sobel operator is much more sensitive towards high frequency information. So that is why when you try to apply something, to select Sobel, Robert, or any other edge detection method, you have to know the background theory. So if you know, oh, I want to use a simple edge detection method to detect great detail, so for sure you should opt for Sobel. Okay, of course you later on you might have Kenny and some other method, then that would be another case case by case basis. But if you are comparing the Sobel and Robert, so perhaps you should select Sobel. And what is the justification? Is that Sobel is much more sensitive towards the high frequency information. Okay. So it is similar to the Sobel operator, but use what is this? Oh, it is similar to Sobel operator, but use slightly different mask, convolution mask, which is okay. Okay. I think this slide first, followed by this one, a bit typo there. Okay, we look at this first, Laplacian, which is the second order derivative. Sometimes we call it as Laplacian, okay. Sometimes Laplacian of Gaussian, same thing. There are three Laplacians mass, and each represent different approximations of Laplacian operator. So the mass are rotationally symmetric, which means you rotate to get the x and y. The sign of the result, positive, negative, from two adjacent pixel locations provide direction information and also tell which of the edge is brighter. So these are the three different masks. Okay, basically you just rotate in different directions, and of course you can actually build your own Laplacian of Gaussian by using the same factor. For example, -1, -2, -1, and -2, and then -1, 8. You can actually build another LOG by using the same scale. Okay, you can play around with this one. Okay, and check what is the output. As long as, because the theory is always embedded inside the scale, the ratio between the 3 times 3 pixel. Okay, so these are the 3 examples for Laplacian, and the coefficient of mass are mostly 0. If the coefficient is increased by 1, you will get the original gray level. Okay, so the larger the sum, the less processed image is changed from the original image. So which means the sum of it, if it is approaching to 1, which means the output image will be approaching to the gray level of the image. Okay, if it is approaching to 0, which means the edge detection intensity or the significance of edge detection capability will be increased. Okay, so the Laplacian operator is defined as follows. This is the operator. Because this is second derivative, so you would found d2 lah, d2i dx2. Okay, for the previous one you will find only dx, dy, something like that. So the Laplacian method search for zero crossing in the second derivative of the image to find the edge. So isotropic function very susceptible to noise. Filtering required. Use the Laplacian approach. As you can see, the second derivative is much more sensitive towards the noise. So for the Robert Sobel and Prewitt, we are using the first derivative. So if there are noise corrupted the input image, would be a bit less significant. But if for LOG, I mean Laplacian alone, so you might have a very bad output image in terms of edge detection. So also called a Mexican head operator. This is another name lah. Okay. Step as follow: noise filtering and smooth the image enhancement and edge detection. Okay. So anyhow, this is the basic steps in the edge detections lah. Okay. Image, then you have filtering. Sometimes you can put in enhancement here. And the operator and your edge map. So Kenny edge detector, which is the motivation from the previous one. So using first derivative and second derivative alone is not good enough to locate edge. So first derivative give a thick edge. Why thick edge? Because you have only this return only this kind of first derivative profile. So that is why you have a thick edge. And the second derivative give too much of ring. Sometimes the ring shape is, the ring is like something that we observe from the second derivative. You might have something like ring shape over there, because the nature of the second derivative is able to detect the curvature of the subject. So sometimes you might find that why this image got so-called the ring shape over there. So this is the one of the shortcoming for the second derivative. So the goal here for the Kenny method, Kenny edge detection, the goal is to mark as many real edge as possible, and the detected edge should be as close as the real edges. So use multiple stages to detect a wide range of edges, and use the first derivative of an image and take the gray level as input. So basically most of the time we are using the gray level to process. Eventually you are in RGB. Eventually the MATLAB algorithm accept RGB image. It is still processing in individual, which means the R layer, G layer, and B layer. Okay, process each of the layer individually and then later on combine. Okay, so this is actually how MATLAB doing. Okay, but I believe the MATLAB do not accept, edge detection in color image. I think need to convert to gray level, or you get the R layer, G layer, and B layer, and then later on perform edge detection in each layer and then combine it. Okay. Kenny edge detector is probably the most common used and most effective method because it's much more complex edge detection method than the one described before. So basically, Kenny is the optimal, what we call as an optimized edge detection algorithm. Okay, so the objective of the Kenny is to low error rates, which means it's trying to suppress all those noise with a very low low faulty edge, low faulty edge. So all edges should be found, and there should be no serious response. And each point should be well localized. The edge located must be as close as possible to the true edge. That is, the distance between a point marked as the edge by the detector and the center of the true edge should be minimum. Which means if you have a transition, RAM transition, something like this one, so the edge after the first derivative, you will get something like this one, right? Okay, so the one of the purpose of the canning is to get a thin edge, whereby the edge is actually located at the center of this thick edge. Okay, Okay, sorry for the technical issue. I found that my my screen is not connected just now. So yeah, and I draw a lot already. Okay, so should be able to listen to, yeah, should be okay. Okay, so sorry for the technical problems. Now everything should be all right. Thank you for notifying me. So let us recap a bit, especially on the difference, especially on the differences in terms of the different types of uh where am I? Okay, different types of the ages. So this is the, let's say you have the original one which is the age lah. Okay, the orange color is the age. So for Robert and Sobel, you were able to get a thick age. Okay, but Robert and Sobel, why we can get a thick age is because Robert, Sobel, and also Prewitt, they are actually only apply calculate up to first derivative. Okay, but for LOG, for Laplacian, it is the I mean calculate up to second derivative. So you will get a thinner age because this is the first derivative and this is the second derivative. So you're able to get a thinner age. Ideally, you should able to get the age which is at the center point of the age lah. Okay, but LOG may not be always get the point at the center. Okay, because the second derivative is meant to detect the directions of the age. So the Kenny is meant to get the edge which is thin and also located at the center of the original edge. So this is the, I mean, how superior is Kenny as compared to Robert, Sobel, Prewitt, and also LOG. Okay, so single edge point response, the detector should return only 1 point for each true edge point. That is the number of local maxima. Maxima is actually maximum. Around the true edge should be minimum. This means the detector should not identify multiple edge pixels where only a single edge point exists. So the last bullet point is actually mentions that, for example, you have only one edge. For example, this is let's say this is only one edge. Okay, the orange color is the edge. But in fact, you're able to get three edge. Okay, so this is what the Kenny trying to avoid. So the Kenny will also compute that, oh, this is only, I mean, all these three lines is considered as one line. So from here, they will select the center line, which is most best, I mean, the best fit line according to this one. Okay, so this is how we actually, uh, I mean, why the Kenny is being used. So step as follow: smooth the image with Gaussian filter to reduce the noise, compute that gradient of using any of the gradient operator, Sobel or Purit, and extract each point, which is a non-maximum suppression point, and link the threshold with hysteresis. Okay, the something unique in terms of Kenny is that it has a hysteretic thresholding, which is a two-layer threshold value. This is the thinning and linking. So you will get something like this one. And choosing a magnitude threshold. If you have a very high magnitude of threshold, you will get many noise. Okay. If you have a low threshold value, you might miss many things. Okay. All the window already missed. So basically, these are the steps of the Kenny detection. So 6 steps. First of all, noise is filtered up. Usually we use a Gaussian filter. But of course, if you want to use any other different type of filter, would be okay lah. Okay. But most of the time, and I think by default, the MATLAB is using Gaussian as well. So find the edge strength and find the edge direction. So you have x and y derivatives to find the direction. Basically, this is the gradient, and then you get generate the magnitude of the gradient, trace the edge as per the direction. So if in order to trace the direction, you need to get the second derivative. So non-maximal suppressions. So which means if this is, I mean, if the Kenny detect that this is an edge, but this edge is not maximum, so it will suppress it. And if this edge is a maximum, so it will declare, oh, this is an edge. Okay. So basically, they are trying to set the condition to know if this is a real edge or not. Okay, so let me repeat. Step 1, 2, 3 is more or less similar than the previous one. Step 1, remove noise using filter. Step 2, find the edge strength. Step 3, find the gradient and also magnitude. Gradient is to find the x direction and y direction, and the magnitude is to get the intensity of the edge. And then step 4, second derivative to get the directions. Okay. Step 5, non-maximum suppression. 5 and 6 will be unique for Kenny. Okay. So step 5, non-maximum suppression. So it will try to suppress those edges which is so-called not the true edge lah. Okay. And for step 6, you would have two different kind of value, threshold value, which is high and low. So that the main purpose of using this threshold value is to optimize the edge detections. Okay, so this is the input image followed by Fourier operator, and this is the Kenny. As you can observe, when we compare Fourier and Robert, we will find that Fourier is much more because Fourier is much more sensitive towards the high frequency information. So the texture of the hair, the face, the wrinkles, the texture, the vertical line of the wallpaper is much more clearer when compared to Robert. Okay, so when we compare Fourier and Robert, we will take Fourier as the best one. So later on in this stage, we will compare Fourier and Kenny. Okay, so when you compare Fourier and Kenny, you will find that the output image of the Kenny is much more clean. I would say the entire image is much more cleaner. Okay, so the texture of the hair is there. In Kenny, the texture of the hair is there. The texture of the wallpaper is there, and the line, all the fine line, the reflections of the hair, the hand, the hair, and this and that, all are quite clear. Okay, but nonetheless, this, the result here will be based on these two, the TH and TI, which is a high threshold and low threshold. If you set a wrong high threshold and low threshold, sometimes the result could be worse than this one. Okay, because you will have to know, if you don't know how to capture an image, maybe mobile phone is the best choice for you. If you're very expert in capturing the image, maybe you should use a DSLR. Okay, if not, I give you a DSLR, you don't even know which button to capture the image. Okay, so this is the trade-off lah. Okay, one is for layman, then you go for Robert, go for Fourier, go for private. If you want to a better result, optimized result with much more more parameter to tune, then you go for Kenny. Okay, so this is the input image and the difference when you set different threshold. So if you have low threshold, so very coarse scale. So the scale of the butterfly or the moth is very coarse, okay, which means only significant line, for example, this can be detected. Okay, but all those other fine line cannot be detected. Okay, so when you have a high threshold, so you will get something like this one, and this is high threshold as well. Of course, you need to fine tune the threshold in order to get the desired image you want. If the threshold is too high, perhaps you will get all those noisy line as your output image. Okay, so you have to be aware in how to choose the value. But what you need to know is that what would happen when you choose a low threshold, and what would happen if you choose a high threshold and somewhat very, very high threshold. Okay, so this is the input image, and this is when you set the threshold as 15, and this is when you set the threshold as 5. So when you set the threshold as 5, you might find that all these are noises, because these noises could be due to the when you read the x and y directions in step 3, I think. Yeah, step 3. So basically, can you all see that this image, there would be a shading here. This is darker and this is brighter. So this shading is actually, if you read the x and y direction and the threshold is not suitable, you might get noise over here. Okay, this is actually the noise obtained from here, the shading from the brighter bottom part and the darker upper part. Okay, so this is you have to fine tune lah. So problem if the threshold is too high, very few or none edges or high misdetection with many gaps. And if the threshold is too low, too many edges, so which means high false positive. False positive is that this is not an edge, but you said it is an edge. So that is called false positive. Okay. So hysteresis threshold can be used for both the high and low threshold. So keep both a high threshold and low threshold, and any edges with the strength less than L. L is low threshold, H is high threshold. Discard. So those with the strength less than the low threshold is being discarded, and those with the high threshold, this is kept, and this is with condition. So which means yeah, very clear lah. This one I think I don't need further explain. Okay. So lower than low threshold will be discarded. Greater than high threshold will be kept, and this one is a condition based. You can declare your own condition. Depends on your applications. So hysteresis is a way of linking the broken line produced in the previous step. This is done by iterating over the pixel and check if the current pixel is an edge. So if it is an edge, then check the surrounding area for edge. So basically, this is also Canning is also the local filtering method, which means you will check for this one, each and every pixel. If this pixel is an edge, if this is an edge, so you will build a window to check the surrounding pixel if there is any other edge. If there is another edge here, so you will link this together. But also this is depend on the window size lah. If you have a greater window, for example, 5 times 5, so if let's say you have a gap over here, so you found that, oh, this direction and this direction is the same, so you can link this together to form an edge. Okay, so that is why when you use Canny, you will find that the continuity of the line will be much more smoother and better than Sobel and Robert. Okay, because it has this hysteresis to join, to continue, to link the edge together. Okay, so if the pixels are greater than the lower threshold, this will mark as an edge. If the pixels are greater than the lower threshold and also greater than the higher threshold, this will become a strong edge. Okay. So which means you have a strong edge lah. For example, this one is the strong edge lah, and this might be the weak edge, and this is not an edge. Okay. So this is the condition being set. So you can actually use the Canny in the MATLAB. The same thing, H, I is an input image and use Canny. And you can actually set the threshold here. The threshold here, the first element shows the low threshold and the second element shows the high threshold, which means you can put this as something like this, EDGE, your input image, Canny, and then you have low threshold and high threshold. Okay. Based on this one, low threshold and high threshold. If you, of course, if you have a better, a higher, new version of MATLAB, you have to check the part syntax to check if it is the same. So this is again, this is the input image. This is threshold 15. This is threshold 5. So if you have hysteresis, so you have a low threshold, which means the high threshold is 15, low threshold is 5. So this one is kept, this is discard, and this is with condition. Okay, so you will get a clean and better image, okay, whereby you don't have very, this is very coarse, which means many edge is being removed lah. But for this one, you have many noise, but for this one will be quite clean. The image is much more clean and sharp. So the application of Canny edge detection could be detect shape and size, video surveillance, traffic management, Canny edge detector for remote sensing. Remote sensing is an application where you're using the drone, the GPS, all sort of this one. So that we call it as remote sensing. Okay. So any questions so far for chapter 4? The entire chapter for image manipulation. Let me check. Any questions? Those from online, any questions? If you have any, if you found any difficulties, especially technical issue, humming this and that, please let me know. Because I may not know if the voice quality is good, if the uh, any other technical issue. Do let me know. Okay. Any question? No. Okay. So that's all for chapter 4. Chapter 5. One moment. Let me get chapter 5. So. Okay, I already uploaded chapter 5 in the Google Classroom, but today I don't think I will start to start to teach chapter 5. But I will give introductions for chapter 5. Okay. So basically, chapter 5 is about image transformation. Although in chapter 4 we did learn about image transformations, but the chapter 4, what we learn about image transformation is, sheer transform from one location to another location, invert, crop, this and that, rotation. Those are, to transform the image from one location or one pattern or geometrically transform. Okay, but for this chapter, we are actually talking about these 3 types of transformation. Of course, there are many more different types of transformations, but these 3 are quite common in terms of image processing. Okay, I believe you all heard about Fourier Transform already. To be frank, last time during my undergraduate, I did learn about the Fourier Transform, but I don't know what this is meant for. Okay, even after I graduate, I still don't know what it is. I'm quite familiar with Fourier, these people, but I don't know what this is for. Okay, so DFT, DCT, and DWT are 3 different transformations whereby you transform the spatial domain to another domain. Okay, the spatial domain is the one in image with which has x axis and y axis. Okay, so since we are dealing with spaces, so we call it a spatial. Like anything we deal with space, we call it a spatial. So for spatial domain, we have the image. In the spatial domain, we can actually look at the image and we can understand what is the message delivered by this image. But in frequency domain, for example, Fourier cosine and also wavelet, you may not able to see the image or look at the image and you can tell what it is. Okay, so this is the difference there. But nonetheless, for Fourier transform, cosine, and wavelet transform, you can have a better features value. So, for example, to train the deep learning model, you can actually get the information from DFT, DCT, and DWT to extract their features accordingly. Because in frequency domain, it would have a difference difference, the same highlight different level of information within an image. As I mentioned just now, all high frequency information is referring to the contrast, the age, the texture, the fine detail, the January line, and this and that. And for low frequency information, it is more on the core information, for example, red apple. So you were able to see the red color, the background, the course line, this and that. They are all considered as low frequency informations. Okay, so let me give you an example. So this is Lena. Lena is the name of this image, which is one of the default image in MATLAB. So in spatial domain, you can actually see that, oh, that is a lady with hat over there. But in frequency domain, I don't think you can see any lady over there. Okay, so this is the image displayed by the frequency domain, whereby the left image is the left side is the spatial domain, the right side is frequency domain. So in frequency domain, basically you cannot tell that this is an image with a lady inside. Okay, so another example would be this one. So this is the Fourier. This is so-called the Fourier Transform. So this is Fourier. So the real image, which is the one in the left hand, at the left hand side, and the right hand side is the Fourier frequency, frequency domain, or the Fourier Transform. So the one those information located at the center is the low frequency information, and those located at the outer part, outer part of, I should use this one. Outer part is the high frequency information. Okay. So of course, not there is no any solid line said that, oh, after this line all are high frequency. No lah. It is just like a graph, this is considered low, this is considered high. That's all. Okay. So approaching to the center origin is the low frequency. Approaching to the boundary of the image is the high frequency information. Okay. So what happened when you rule out or sort out some of the information? So we have this one. If we mask out all the high frequency informations, so you can, this is your output image. Okay. This is the ori image, which means it is quite clear lah. Okay. All the texture, the line, the eye, the eyebrow, this and that, all are quite clear. Okay. And when you mask out all the high frequency information, remain only the low frequency. Of course, most of the low frequency informations, you will still able to recognize, oh, this is Fourier. If you don't know this is Fourier, at least you can tell this is a male, right? A man, English man. But nonetheless, you cannot see all those fine texture on his clothes, the hair, the very fine texture of the face, this and that. Okay, but when we try to mask out all the low frequency information, remain only the high frequency information, you found that this is the output image. Okay, this is the output image. So if you know this is, the original input image is this one, perhaps you're still able to recognize, oh, this is a male, okay. But to be frank, by looking at this image alone, you might say that this is a grandmother with a curly hair. Okay, so that is something different. You can no longer tell that the message behind this image. So that is why I hope from here, at least you all know what is the difference between high frequency information and low frequency information, where I mentioned just now. Okay, we come back. Robert might be able to detect age, and the age usually is very thick. Why? Because it is first derivative. And Sobel, it still can detect the age and using first derivative, but it is much more sensitive to high frequency information. Okay, so if you were, if the question asks you to detect age using this image, perhaps Robert and Sobel would result. You would give the similar result because high frequency information already being removed. Okay, but if you have the original image like this one, if you want to choose between Sobel and Robert, perhaps Sobel would be better lah. And of course, if you want to compare between Sobel and also Kenny, perhaps Kenny would be better lah, because the Kenny would determine the second derivative and etc. So of course you would have a first derivative followed by second derivative and followed by optimal, which is the Kenny. Okay, so this is just to give you all rough idea on what is high frequency information and low frequency information. We will learn this in depth in next lecture, which is this Thursday. Okay. And a warm reminder, this Thursday we have 2-hour class, which is from 1 to 2 to 3. Okay. And the first class is in M202 and then later on M203. Okay. Just one class next to it. Okay. So I think that it is for today. Any other questions? If none, so that's all. Okay, thank you so much and bye bye.